Hi, welcome back. Um, Last time I was talking to you about a simple N-nary tree design, and then we had discussed various examples and looked at the operations. And where we left off was with respect to the time complexity of this implementation. Just to recollect, this implementation is nothing but a list of these nodes. Every tree node is looks like this, and it has a list of its children IDs. It doesn't have a list of, again, its children nodes, but only the IDs. And then we look up the node based on the ID. So essentially, all the nodes are just an array or a list. So if you want to do a single node related operation like adding a new node, or you are finding a matching node and things like that. So the order of operation will be the order of number of nodes. So essentially it will be order of n. But if you're doing, what about removing a node? Removing a node, just the node itself is order of n, but then you will have to go and remove its children, and the children have further children, so it will keep cascading like that. So that's essentially nothing but a subtree operation. That's how I'm viewing that. So let's look at what is the time complexity of a subtree operation. So what does a subtree operation involve? Say you're just trying to print a subtree. So let's start with the root. Then what it involves is finding, start from the root. So root is obvious. Then you go to each of the children from the root. Then after that, how you find each of the children? You basically have to again look up the children in the list, because we have the root will have the children IDs. So finding, if you're just looking at any other subtree, then first you need to find the parent node that you're looking for. So that's essentially order of n. And then assuming that it has another max n children, then finding each node in that list will be further n into order of n. And then the total time complexity then would be finding the parent plus each of the children. So that's n plus 1 into order of n. That's fairly around n into order of n. So let's use this as a basis and then look at a simple example. Let's look at n equal to 3, wherein, and you have, say, 3 levels, and I'm using zero-based index, so level 0, level 1, level 2. And referring to this diagram, let's start at root, which is at level 0, and then there are 3 children at level 1. So from the previous slide, just to print children of one node, the time taken will be n into order of n, which is nothing but 3 into order of 3. So finding 1 is going to take order of 3, then another one, then another one. So just from root, if you start off, it will be 3 into order of 3. Now the same thing will apply if you start from 1 and then 3 children for 1, 3 children for 2, 3 children for 3. So at the next level, the total time taken is going to be 3 into order of 3. So that's like 3 squared. So the total time taken for this subtree, for this tree operations from root is going to be 3 into order of 3, or we can say 3 power 1 into order of 3 plus 3 squared into order of 3. And that is nothing but, if we generalize it, then it's nothing but 1 is 0 plus 1 and 2 is 1 plus 1. So level 0 and then level 1. So that's nothing but 3 into level plus 1 into order of 3. So generalizing this for N-nary tree, this is nothing but sum of n in n power level plus 1 into order of n over all the levels from 0 to the number of levels. So if you see that this is a lot of time complexity, a large one, it's exponential almost. So, but this implementation will then work better if you are not having a lot of subtree operation to do, but with more of quick lookups. The implementation design as well is simple, and this, let me tell you, is actually in use in one of the products that I work for. I developed this, so this is a variation. It's not the exact same one, but the overall concept is the same. And I wanted to take you quickly through the implementation. This implementation is available in Git, and I have given the link for that in the description of this video in YouTube. So as I showed you earlier, this is nothing but a collection of nodes, and every node looks like this. It has an ID, it has a name, it has a parent ID, and the data, and then a collection of children ID. So in C++, I've tried to use the data as a template. So this is nothing but a template class so that you can pass any kind of data to this tree, so that for each node, there will be a templatized data. And the children IDs is a container again. So you can use either and I said that this tree is nothing but a collection of these kind of nodes. So this class is having this as a container node. So container node is nothing but a list of simple tree objects. You can switch between list and vector by simply, if you want to use vector, you can uncomment this and comment this out and do the same thing here. I just did this because I wanted to see how easy it was to switch between list and vector, and this code fairly works fine without that. And this code has reasonable documentation. You should be able to understand this. I would request you, if you have any questions on that, please reach out to me via comments, or you can also visit the website insync.llc.com and leave a comment for me there or on the YouTube. Thanks for watching this. I'm going to add further videos for describing how to have more tree data structure operations and also graph implementation. This was just for an N-nary tree, but this Git repository also has the implementation of a binary tree. And this CPP has various operations done using this class. So I hope you will find this useful. Thank you for watching this, and I will come back with some more videos. Bye-bye.